Now I'm going to give you a checklist of what I should know when I talk about acid and base. The first thing is to be able to define that we cannot negotiate. Definition of acid and base. I'm just going to list the things we should know here because of time frame. Acid and base, and we know we have two definitions. We have Arrhenius and Lowry-Bronsted. All right, you do have all those definitions with you. Number two, you need to be able to talk about the strength of the acid. So we talk about what is a strong acid, a weak acid, a strong base, and a weak base. So strong and weak acid and base. Number three, you need to be able to talk about dilute and concentrated. Dilute talks about more water than the acid. Concentrated talks about more acid than the water. But there's one thing that I need us to quickly know, that the number of moles of the dilute substance will be equal to the number of moles of the concentrated. And that you can then say CV of dilute will be equal to what? CV of concentrated. That's a very key point when it comes to calculation. Number four, we need to be able to talk about conjugate base, conjugate acid and base pair. All right. Number five, I'll probably go back to the strength as we go into questions. Number five, be able to deal with, before you even start dealing with calculations, deal with proticity of the acid. All right, you talk about a monoprotic acid, a diprotic acid. All right, so we need to know which acids are monoprotic and which ones are polyprotic. And please don't forget common examples here. Make sure you know a few common examples. I'm just going to go into calculation because of our time frame. I wish I had enough time to deal with the summary of all of this like I've been doing for other topics, but it's quite long. Let's just quickly look at a question. Oh no, not this one. Let's look at a question here. All right, while answering this question, I will then deal with the summary as well. Okay, let's have that, and I will move this over. So know your theory. Calculation is actually the easiest once we get our theory in place. All right. Now, define a base. Look at the first question. Define a base in terms of Arrhenius. We said that. All right, 7.1. A base is a substance that does what? Produces. This is why I didn't want to just waste time there. Produces hydroxide ion when it ionizes in water. So it changes into ions in water. If it was an acid, let me just quickly do that here. If it was an acid, what this is to, let me change the color. If it was an acid will then produce what? Hydronium ion when ionized in water. Hydronium ion is written H3O plus. Hydroxide ion is written OH minus. Beautiful. Explain how a weak base. Guys, if you check my summary, the list I gave you, basically we're following that order. All right. Explain how a weak base differs from a strong base. And I'm going to do a crash summary here quickly. Weak acid and strong and weak base. Let's do the summary here. This is where I am going to do my crash summary for you. All right. Weak base, and so we have a weak base. Let me just get good. And a strong base. Now, both of them will do what? Will produce hydronium ions, but a weak base will ionize partially in water, while a strong base will ionizes completely in water. And when it ionizes partially in water, what does a weak base do? It ionizes partially to produce a small concentration of hydroxide ions. While a strong base will ionize completely in water to produce a high concentration of hydroxide ions. Very key. That's the first thing. A weak base, you have Kb is less than 1. A strong base, Kb is, remember we talked about Kc. Alright. Kb is less than 1 and Kb is greater than 1. For a weak base, then you have the reverse reaction favored. So if I have XOH, the reverse reaction is favored. X plus OH minus. If I, for a strong acid, this is what I will then have. The forward reaction is favored. Okay, common examples. We have ammonia, carbonates. Your carbonates are examples of weak bases. What about a strong base? You have metal hydroxides, except for magnesium hydroxide. So when you have your metal hydroxide, anything metal, your aluminum hydroxide, sodium hydroxide, potassium hydroxide, all of those except for Mg, because Mg doesn't dissolve well in water. So I can come here and put MgO2, OH2. All right. So, I mean, we've over answered that question. Let's go on quickly. A learner wishes to identify element X in the hydrogen carbonate. So we have XHCO3. To do this, she dissolves XHCO3, 0.4 grams of that, in 100 cm cube of water. All right. She then titrates all of this solution with a 0.2 moles per dm cube hydrochloric acid solution. Methyl orange is used as an indicator. I want us to go back. A learner wishes to identify element X in the hydrogen carbonate. So we have XHO3. Let's try to get a fresh page. So this learner has XHO3. Okay. Let's go back. Now, to do this, she dissolves 0.4. So we have the mass in 100 cm cube of water. All right. So what is my mass? 0.4. What is the volume? 0.1. Remember, we divide by what? 1,000. Beautiful. Okay. What happens? Okay, she then titrates all of this solution with 0.2 moles hydrochloric acid. Okay, moles per dm cube. So we have the concentration of the hydrochloric acid. We have HCl, and concentration is what? 0.2. Beautiful. So I'm extracting all the information out as I read. Methyl orange is used. Okay. Calculate the pH of the hydrochloric acid solution. That's very straightforward. So the first one, pH would be what? Negative log hydronium ion concentration. Mind you, this is a monoprotic acid. So if it's a monoprotic, it's a ratio of 1. My pH therefore would be negative log of what? 0,2. And what is that answer going to be? Negative log of 0,2. Negative log of 0,2. We close the bracket. We have 0,69. All right, 698, which is 0,7. Now, please take note. If it was something else like sulfuric acid, let's just do a crash course here. If I were to look for that, then my pH would be equal to negative log 2 times 0,2. Please take note. Diprotic. We have 2 moles there. So take note of that and then you get your answer. That was a good crash course there. Okay. Give a reason why methyl orange is used. You must know your indicator selection. Indicator selection. There are 3 types of indicators, so I'm just going to do my indicator selection here quickly. Indicator selection. I always call it my beautiful princess. My beautiful princess. This is methyl orange, bromothiamyl blue, and phenolphthalein. All right, phenolphthalein. So my methyl orange, because of my pH scale, I started acid, then neutral, then what? Basic. Now, when do I use this? When I have a strong acid and a weak base. You see, my acid is strong, so my salt would be what? Acidic. Here, when I have a strong acid and a strong base, weak acid and a weak base. This is why you must know common examples. And for bromothiamyl blue, I need something basic, so I'm going to have a strong base and a weak what? Acid. The base is strong. So the question examiner says, why are we using methyl orange here? We use methyl orange because, so we use methyl orange, and I've answered that now already, because we have a reaction between what? A strong acid and a weak base. I told you that carbonates are bases. Hydrochloric acid is a strong acid, and whatever carbonate this, hydrogen carbonate this, it is a weak base. Carbonates are weak bases. Beautiful. Okay, I hope that also helped you there. Now, let's just quickly look at this calculation. At the end point, she finds that 20 cm cube of the acid neutralized all. Guys, when you see neutralized, run straight to your Na over Nb. All right, all the hydrogen carbonate in the reaction. Oh, and we have a balanced reaction. Basically, it's 1-to-1. Identify element X. We are now given the volume of the acid. I'm going to clone this page because I need all the information. We are now given the volume of the acid. Let me come here quickly and clone my page. Great. The volume of the acid is 20 cm cube. Remember what we said, guys. Do not calculate in cm cube. All right, divide. 20 cm cube would give you 0,02. Now, because they talk about neutralization, guys, I know that, and I have 1-to-1. So the number of moles of the acid is equivalent to the number of moles of the base, which means here, guys, what is missing? All right, because this is, we're given mass here. I can then calculate the number of moles. Remember, I want element X. All right, so number of moles of the acid would be what? CaVa. What is my C? 0,2. What is my V? 0,02. And what would this give me? 0,004. You can always confirm because of the zeros. First, we said 20 divided by 1,000. All right, 0,02 multiplied by 0,2, and that gives me 0,004 moles. Now, mole ratio. If you remember, we followed the same process when we did rate of reaction. What is my mole ratio? 1 mole, okay, X, let's write X, H, CO3, and hydrochloric what? Acid. 1 mole will produce 1 mole. But how many moles do I have? I don't know this. I have 0,004. It means the number of moles of the base is 0,004. Beautiful. Number of moles is 0,004 moles of the base. Which means, guys, I can now calculate my mass. Number of moles is mass over molar mass. Alright, number of moles is 0,004. Do I know the mass? No. Now, what about the molar mass? I do not know what X is, by the way. Alright, but I do have my mass. My mass is 0,4. Lovely. Now, but I do not know what the molar mass of this particular substance is. That's where my problem is. All right, but let's throw all of that in. Hydrogen, we don't know X, so I'm going to say X plus hydrogen is 1, carbon is 12, oxygen is 16 times 3, which gives us what? 48. Let's do the maths. 48 plus 12 will give us 60. 60 plus 1 would give us what? 61. So we have 0,004 equals to 0,4 plus 61 plus over 61 plus X. All right. We can then cross multiply 61 plus X there. Just get a page as we round up. 61 plus X multiplied by 0,004 equals to 0,4. Does that make sense? Yes. There are other ways of getting this answer. Let's deal with this. 61 plus X therefore is 0,4 divided by 0,004. Let's use a calculator so that we are sure. 0,4 divided by 0,004, that gives us 100. Beautiful. 61 plus X equals to 100. What is X therefore? 100 minus 61 would give us what? 39. And if you go to your periodic table to look for the element that has this atomic mass, you would find that it is potassium. So X is potassium. And that's how you work through your acid and base. All right. Now, I won't just run away here. I'm going to tell you how to deal with your percentage purity, which is mass of pure substance over total sample of impure multiplied by what? 100. This is the trend, and I'm going to quickly show you the trend. You will be given a compound A plus B to give you C plus that. Now, you will be told that you want to find the percentage purity of B, for instance. Now, so you need that formula. But here's the thing. They will not give you the mass. Please follow what I'm saying. Mass will be missing because you need the mass to get percentage purity. So mass of this will be missing. How do you get mass? Number of moles is mass over molar mass. Watch this. It's a back trace reaction. All right. So you want to get the mass. Of course, molar mass you would have from the compound. But now to get the mass, you will need number of moles. How do you get this number of moles? You are going to work with mole ratio from the number of moles of this one. Now, so this is the trend that examiners would give you. In most cases, they will give you two reactions. Watch this. This will be your first reaction, and this will be your second reaction. Now, you see this A will come into the second reaction and will go through a titration in most cases. When you see complete, especially when you have complete neutralization, then you are going to use Na over Nb equals to what? CaVa over CbVb. So check this. So you are going to take this particular A, this A is given to you and reacted with something else. I'm just going to say Y to give us X plus Z. Watch this. So you have two different reactions. This is how you are going to start. This is the trend. Start with the second reaction. Start from 2. And work with A, because A is what's common in both of them. Now, when you work with A, you are going to find the number of moles in A. After doing that calculation, you will take the number of moles here and work with the mole ratio to get the number of moles here. When you get the number of moles here, you are going to get the mass here. You put that mass here and you calculate your percentage purity. You're looking at 8 marks. I would repeat. Whatever the situation is, if you're given something like this, you need to see A and A, work with what's common. If it's a complete neutralization, work with this. This would allow you to get whatever it is. Your aim is to get the number of moles of A. Now, the number of moles of A, whatever it is, you are either going to subtract or what, in case it's in excess, all right? Check on our YouTube channel. We have quite a series of acid and base questions that we've dealt with, and we've dealt with things like this. Time will not allow us to go into in-depth, but please check Crazy Edu TV. You would have a lot to deal with there. So you have your number of moles. You get the number of moles here. Mole ratio allows you to get the number of moles. When you get the number of moles of B, you get the mass. You bring the mass in and calculate your percentage purity. All right, I'm really running out of time, but I hope that this has been helpful. All right, I will catch you in the next question where we deal with electrochemistry. I hope this has been fine. Again, please download the video from YouTube and watch over. Don't watch on YouTube, we wasted a lot of data. Download and watch over and over again. All right, this is acid and base simplified. Awesome stuff. Okay.